Hi guys, today we're going to talk about verifying inverses. So if you'll remember, we talked about inverses a few sets of notes ago. We talked about how inverses, when you graph them, are reflections over the line y equals x. We also talked about how if you're given an equation and you need to find the inverse, then you need to switch x and y and then solve for y to get your inverse equation. So today, I'm going to talk to you about how you can verify that two functions are inverses of each other. So there are two ways to do that, two ways to verify whether or not two functions are inverses of each other. The first way is graphically, and this is a way that we already kind of discussed, so we're going to bring it back to the forefront of your mind. Because we did go on a tangent for a couple days and talk about composition of functions, which we are also going to use here today. But I want to kind of bring back this whole reflection over the y-axis business. So graphically, if you have two functions on a graph, and those two functions are inverses, then they will be reflections of each other across the line y equals x. Now, in order to determine if two functions are inverses of each other graphically, the first thing that you need to do is graph the functions. You need to put them on the coordinate plane. So graph the two functions. The second thing that you need to do is you need to graph the line y equals x. Or you can rewrite this as y equals 1x plus 0. Because it means the same thing as y equals x. It's the linear parent function with a y-intercept of 0 and a slope of 1, or 1 over 1, to help you graph. So in our example, we're going to have the two functions graphed for us in this problem. We're going to have y equals x graphed for us. And then the last thing that we need to do is verify that they are reflections. Verify that they are reflections. So kind of count diagonals to the line y equals x and past the line y equals x. So in example 1, I'm asked to determine if the following graphs are inverses of each other. So we have this graph and we have this graph. They're already graphed for us. So in order to graph the two functions, I don't have to do anything. Step 2, graph the line y equals x, or y equals 1 over 1x plus 0. So we have, I'll use blue. We have a y-intercept of 0, and I go up 1 over 1, back on my line. Up 1 over 1, back on my line. Up 1 over 1, back on my line. So this line right here that's dashed, that's the linear parent function, y equals x. It's already there for us. And then finally, I need to verify that these are indeed reflections. So with every point that I'm given, I want to make sure that there is a point on the other side of y equals x that mirrors it. So I'm going to count diagonally to the line of reflection. So here I count one unit, one diagonal box to the line of reflection, and one diagonal box past the line of reflection. I end on my other graph. So this is looking good. I'm going to do the same thing with this point. So I'm going to count diagonally 1, 2 diagonals, and pass the line 1, 2 diagonals. Both of these are good. And I'm going to do the same thing with this point. So I'm going to count past 1.5 diagonals, and then 1/2 and 1 diagonal. So this point is also good. That tells us that this function, so my video, when it stopped, and so I have information on here that I'd already gone through, but then I had realized that my video had stopped. So I want to make sure that I go back through and talk to you about actually what I just said in real time. So I'm trying to decide if this point is reflected over the line y equals x to give me this point. And so that's happened here. I go 1, 2 diagonals, and then 1, 2 diagonals. This is good. Then I do the same thing with this point, 1.5 diagonals, and then 1/2 and 1 diagonals, and I end up back on this curve, which is good. That's what I want. So I've determined that yes, these two graphs are inverses of each other because they're reflections of each other over the line y equals x. And I apologize if that information was kind of spliced together, or maybe you got repeated information, but I didn't realize that my video had stopped. Okay, so graphically, you need your two functions to be reflections over the line y equals x. You graph your functions, you graph y equals x, and you verify that they're reflections of each other. If you count diagonally and then count diagonally again and you don't end up back on your second graph, then that means you don't have inverses. So let's look at number 2. Number 2 says determine if the two functions are inverses by graphing, and it specifically says we need to determine if the functions are inverses by graphing. So that means I do have to graph. We're going to talk about another way to verify inverses today, but if it tells you you have to do it by graphing, then you have to do it by graphing. So the first thing I need to do is graph the two functions. This is y equals mx plus b. My b value, or my y-intercept, is 2. So here we go. And my slope is 1/3, so I'm going to rise 1, run 1, 2, 3, rise 1, run 3, rise 1, run 3. I'm going to do the same thing backwards, down 1, left 3, down 1, left 3, down 1, left 3. I'm going to use a straight edge, and you can use your drawing tool to give yourself a nice straight line here. And I need to do the same thing with my second graph. So I'm not going to annotate it as I do it. I'm just going to go ahead and graph the g of x function, which is g of x equals 3x minus 2. 3 over 1, 1, 2, 3 over 1, 1, 2, 3 over 1, 1, 2, 3 over 1. Same thing backwards. Using my straight edge. I say I'm not going to annotate, and then here I am annotating. Sorry, I think out loud. Okay, so we graphed the two functions. Now we need to graph the line y equals x, or y equals 1 over 1x plus 0. So I'm going to go ahead and plot my y-intercept. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. I keep going because this is the parent function of all linear functions, y equals x. So I'm going to kind of make this a dashed line here because it's not really part of my functions. It's just how I'm going to identify if these are inverses. So I'm going to go ahead and start with this point just because it looks like, I don't know, a nice point to start with. You can really start with any point. But make sure that you check all the points until you find one that possibly doesn't work as a reflection. So I'm going to count diagonally 1, 2, and I'm going to count past it 1, 2. There is no point on my first graph, my first line, that goes through this point right here. Not at all. So that means that this line and this line are not reflections of each other over the line y equals x. So I'm going to say no. They are not inverses because they are not reflections over y equals x. That is my reasoning. So I told you that there are two ways that you can verify inverses. Graphically is one way, so that's what we discussed today, and it's kind of a little review of what we did on our first day of inverses. But now we're going to talk about how to prove that two equations are inverses of each other algebraically. And so in order to do this, we need to call upon our knowledge of composition of functions that we discussed the previous day and the day before. So algebraically, if functions f and g are inverses of each other, then if you find f of g of x, or fog as some people say, and that equals x, and then you find g of f of x, and that also equals x, then you have inverses. So in order to do this, in order to make sure that both of these equal x, you're going to plug f into the g function everywhere you see an x and simplify. And then you're going to do it the other way around. You're going to plug g into the f function everywhere you see an x and simplify. They must both equal x for the two functions to be inverses. If one equals x and one equals something else, then they're not inverses of each other. So I have two functions. I have f of x and I have g of x. First thing I need to do is to determine what f of g of x is. So in order to do that, I'm going to write my f function, but instead of x, I'm going to put parentheses so that I can put my g of x function in there. So 2 times x, so a big blank space, plus 4. And then inside of that x for the f of x function, inside here, I need to put the g of x function, so 1/2 x minus 2. Okay. When we try to simplify, because we want to make sure that we get x here, f of g of x is equal to 2 times 1/2 x, which is 1x. Oops, sorry. 2 times -2, which is -4, and then plus 4. Well, what happens with -4 and plus 4? They go away, and you have f of g of x equals x. This is looking good, right? So now we have to check the other way around. Here we checked f of g of x. Now we need to check g of f of x. So I'm going to do the same thing. I'm going to write my outer function, but when my outer function is written anywhere that there's an x, I'm going to leave parentheses so I can put my other function in there. So 1/2 times x minus 2. And inside the g function, I need to use f of x here. So f of x is 2x plus 4. And in order to simplify g of f of x, I have 1/2 times 2x. Half of 2 is 1, so that's just 1x. Half of 4 is 2, and minus 2. And 2 minus 2 is 0, so I have g of f of x is equal to x. Looking good. So I am able to verify that yes, they are inverses. Awesome. All right. So let's try number 4. I'm going to ask that you try a little bit of it on your own. If you're color coding with me, then go ahead and give f of x a color and give g of x a color. If I need to prove or determine algebraically if the two functions are inverses, then I need to check two things. I need f of g of x to be equal to x, and I need g of f of x to be equal to x. So I'm going to help you out at the beginning, and then I'm going to see if you can do the other one. So f of g of x means I write the f function, but instead of writing x, I write a big set of parentheses so I can put the g function in there. So the f function is 3 times x minus 9, and the g of x function that goes in here is negative 3x plus 9. So when I simplify for f of g of x, I get 3 times negative 3x. I get 3 times 9, and I get minus 9. Uh-oh. F of g of x is equal to negative 9x plus, what is that, 18? This is not x. So that's a problem. Even if g of f of x is equal to x, this is not. And so I have to claim that no, they are not inverses. Because g of f of x, well, maybe g of f of x, but f of g of x is definitely not equal to x. Okay. So the last page of our notes today combines the two forms that we have discussed. So we are supposed to determine both algebraically and graphically whether or not f and g are inverse functions, and we have two problems to do that with. So, and notice that problem number 6, the graph is on the next page. So I'm going to do 5 for you, or with you, and you're going to do 6 on your own and check back, okay? So algebraically, I need to determine what f of g of x is. So I'm going to give f of x one color, g of x another color. The outer function is f of x, so 4 times x plus 3. The inner function is g of x, that's 1/4, x minus 3. 4 times a fourth x is 1x. 4 times negative 3 is negative 12. And then plus 3. This is equal to, what, x minus 9? This is not x. So I can claim that no, they are not inverses. Now I was asked to do this algebraically and graphically, so I do have to do it graphically as well. So I'm going to go ahead and graph my functions. My f of x function is 4x plus 3, so I'm going to start at a y-intercept of 3. I'm going to rise 1, 2, 3, 4 over 1, down 1, 2, 3, 4, back 1, down 1, 2, 3, 4, back 1, down 1, 2, 3, 4, back 1, straight edge. And then my g of x function is 1/4 x minus 3. So I start out at minus 3, 1 over 1, 2, 3, 4, 1 over 1, 2, 3, 4, down 1, back 1, 2, 3, 4, down 1, back 1, 2, 3, 4. Straight edge. And I need to graph my line y equals x. So I'm going to go ahead and do that, starting at 0, 0. And I graph each diagonal because that's a rise of 1 and a run of 1. So here is my linear parent function. And now I need to determine if they are reflections. So I'll pick a point, maybe this point. I'll go 1, 2, 3 diagonals and 1, 2, 3 diagonals. There's no point here. So that tells us that no, they are not inverses. Graphically, they are not inverses, and algebraically, they are not inverses. So I want you to use this. I want you to try number 6. Remember that the graph is on the next page. Pause your video, and I'll show you the answer in a moment.